So this is our first video cast of Chapter 17, Additional Aspects of Equilibria. In this chapter, we'll look at 4 different areas. One called the common ion effect. That'll happen during this video cast. Buffers, how they're made, what their pHs are. Titrations, a deep look at those. And the aspects of equilibria involving soluble things that are pretty much insoluble, where a tiny bit of that dissolved substance can make a difference. So here we are in the common ion effect. It's chapter 17, section 1. And the common ion effect is when we have something dissolved in water, usually a weak acid or base, and then an ion that is in common with that. So let's jump right into a sample problem. Let's calculate the F minus ion concentration and the pH for a concentration of HF acid of 0.2 molar, and additionally in this solution we have some HCl at 0.1 molar. So step number 1 when you do this type of problem is to realize that you have a mixture, and when you have a mixture of 2 different solutions, look for an ion that would be in common. And you probably already noticed that this is a weak acid that would have hydrogen ions, and this is a strong acid that would have hydrogen ions. And so the hydrogen ions would be the ion that is in common. So steps on this, step number 1 is to write the weak electrolyte, the weak acid or base usually, with water. And so I did that. I took the weak electrolyte, HF, and I reacted it with water, and I got some H3O plus, and I got some F minus. Second step, after I've written that weak equilibria, is to write an ice table. And once I've written an ice table, look for the ion that is in common. And so I'll put down ICE, leave a little extra space for the I here. And initially, I have a concentration of 0.2 molar for HF. Water is a pure liquid, so it's not going to be affect the equilibria. And then H3O plus is going to come directly from the HCl, because remember HCl is a strong acid, so it will completely dissociate into H plus and Cl minus. And 0.1 of that will be already dissolved in this solution. And then there isn't any F minus present at the start. Now at the change, HF is going to dissociate, and it's going to give me some of this and some of this. And I don't know how much, and so I'm going to use a letter for that. I'm going to say I'm going to lose X amount of the HF, and I will gain an equal amount since it's a 1-to-1 ratio, and an equal amount since it's a 1-to-1 ratio. And then at equilibria, I'll have 0.2 minus X, 0.1 plus X, and X amount. And of course my goal is to find this concentration right here. And then also I want to find this H3O plus ion concentration because I can find the pH from that. So in step number 3 now, do the ignoring of the X. And so say that X is small compared to the 0.2 and compared to the 0.1. Makes it really nice and easy to solve when both of those are gone. And now you can write the K expression and set the K expression equal to the Ka of HF, and I'm going to look that up in the back of the book, or I'm going to look it up in appendix D, and I can set that Ka, 6.8 times 10 to the negative 4th, equal to the products divided by the reactants, and once again ignore the X, ignore the X. And now I can solve this equation. And so solving it then ends up being the X is equal to F minus, bring this over here, bring this over here, and I did the math for you already, which is 1.4 times 10 to the negative 3rd. So I found my F minus ion concentration, and it asked me to find that, and then it also asked me to find the pH. And if you look back at this, notice how I ignored this X because it was small compared to the 0.1 that came from the HCl. And so the driving species for the pH is my strong acid, which isn't surprising because strong acids obviously completely dissociate, whereas the weak acids would just give me a tiny little bit. And 1.4 times 10 to the negative third plus 0.1 wouldn't make a significant difference on that 0.1. And so the H3O plus is equal to 0.1 molar, and I can take the negative log of that and ends up with a pH equaling 1. So this is a real normal common ion problem that has mathematics attached to it to give you concentrations at equilibria. But if you're not given a math problem with a common ion, lots of times you can simply use Le Chatelier's principle to predict this. And Le Chatelier's would have predicted that the concentration, when I have some of this H3O plus ion added to it from the HCl, would have shifted the reaction to the left. And so from a normal weak acid problem where I would solve for this and for this, I would have less of this available because the reaction would be shifted left due to the increase of concentration of H3O+. So in this short video cast, hopefully you learned that common ions shift equilibria, that you can calculate the concentration at equilibria when there's a common ion with ice tables. And you should know that in the future, there'll be many, many more of these mixtures, especially with weak acids or weak bases and their conjugates.